Okay, before we actually dig into this day 4 notes, there's a short reading that you need to do in the textbook. It starts on page 423. It's titled Normal Model to the Rescue, and it kind of sets the stage for why we even need to do this. And it ends at the top of page 424 with a highlighted yellow section before you get to the math box. So if you don't have your book, that's fine. There is a scan of those 2 pages from the textbook on your Schoology. So hit pause and go back and take a look at that little section about the normal model before you listen to the rest of this lesson, because it'll make a little more sense that way. So hopefully you paused and read it. Now we can talk about it. So especially back before calculators were pretty powerful and could crunch some fairly large numbers, there were times that the binomial model was not usable when we had very large sample sizes. Our calculator can handle some pretty large number calculations, but even the numbers that are in that blood type problem that you just read about, our calculator, if you try to calculate some of those combination formulas or some of those powers, some of those exponents, our calculator can't even hold them. It'll go to 0, or it'll just give you an error message and kind of an overload message. So even our pretty powerful machines that we use now can't handle some of those really large calculations like the one that was in the textbook just now. It can actually handle the one we're going to work together, but still, we need to kind of learn this connection. The normal model can be used for continuous random variables where the distribution is fairly unimodal symmetric. Binomial model is used for discrete random variables. So continuous when you have a range of values, discrete when you can list values. So the models are different. One's continuous, one is discrete. However, under certain special circumstances, when certain conditions are met, and you can't compute a binomial distribution or a binomial probability because the numbers overload your machine, a normal model can be substituted under those conditions and get us an answer that's close enough to be useful. And so we need to kind of learn what that looks like. So we'll come back to those conditions at the end of the problem. So I'm going to kind of skip past this for now and go straight to a for instance. So we're going to use a binomial model to answer this question. So we have an airline that thinks that 5% of passengers, statistically in the past, 5% of passengers have failed to show up for their flights. So they overbook. They sell more tickets than they actually have seats because they really want to have behinds in every single seat, because then they maximize the money that they make. Okay, so we have a plane that holds 365 passengers, and they're going to sell 275 tickets. Okay, well, that's 10 extra tickets. Is that more than 10%? Actually, or more than 5%? Well, actually, 5% of 275 is it's close to 14. So, on average, if you sell 275 tickets, you would expect, on average, about 14 people to not show up. And so you would have plenty of seats for the rest who do show up. So they're willing to take their chances, and the people who buy those last 10 tickets are on standby, and they may or may not get a seat. What's the probability that the airline will not have enough seats so that someone gets bumped? So if we have more than 265 people show up with tickets, then somebody's going to get bumped. So what we really want to know is the probability that the number of people who show up for the flight is at least 266. If 266 show up, if 267 show up, if 280 show up, 272 show up, we have a problem because there's not enough seats for those, but they have tickets. So this is a binomial distribution. We have a predetermined number of tickets sold, predetermined number of people who could show up. 275 people potentially could show up for the flight. We want to know the probability that at least 266 of those do. So we're counting successes out of a total 275. That's a binomial distribution. So if we use our binomial formula, if we had 275 potential flyers who could show up with a ticket, and 266 of those show up. There's a lot of ways that can happen. This counts those ways. Multiply by the probability that someone will show up. Now, the probability that someone will show up is 95%, and there's 266 of those. And then multiply by the probability that somebody doesn't show up, that's 5%, and there are 9 no-shows out of the 275 who bought tickets. Or we could sell 275 tickets, 267 people show up, so 0.95 to the 267th power, and then 5% to the 8th power, 8 people won't show up. And so on and so forth until we get to 275 out of 275 all show up with ticket in hand and 0.95 to the 275th power. Now, older calculators, less powerful calculators, calculators with less memory, couldn't handle some of these things in the past, like couldn't even do that combination, or couldn't do 0.95 to the 266th power. Our machine will do that. It's got quite a bit of memory in it. The problem in the textbook, we had much, much larger powers. Our calculator won't even take care of those as individual pieces. But our machine will actually do this computation because it's pretty modern. Of course, we have a shortcut, so we're going to use the shortcut because that is the only practical way. So we're going to go to, let's get a clean page here. Menu and probability or statistics, either one. Distributions, number 5. And we're going to have to go down to binomial CDF, so that's option B. We have 275 trials. 275 people could show up. Of those 275, the probability of showing up is 0.95. At least 266 could show up and be a problem. At most, 275 could show up and be a problem. Actually, the flight that I was on, both of them that I was on back in January, had multiple people on standby. The flight from Charlotte to Pittsburgh actually had 16 people on standby, hoping that somebody wouldn't show up so that they could get a seat. Was happy that I was not one of them because every seat was full. Anyway, that's about 11.6%, so 0.116-ish. Now remember, this is a model, so the probability of not having enough seats for everybody that shows up is about almost 12%. This is pretty high, but it's worth the risk. You make some people unhappy when that happens, but you still maximize your profit, and so there's a balance between the two there. So binomial model works fine as long as you have a calculator that's powerful enough to crunch these numbers, and we do. They can get so large that our calculator won't take care of them, in which case this structure is great when you set it up, but you can't compute it because you don't have a powerful enough machine to do it. So what if our numbers get so big they won't compute it? Or what did they do before we had powerful enough calculators? And so that is the normal model piece of this puzzle. So what we could do is use a normal model instead. And it's going to give us a reasonably close estimate of what we just computed. So if certain conditions are met, and we're going to come back to those conditions, read about them in the textbook, but we'll visit those on the last slide. If certain conditions are met, the normal model will do a decent job of estimating what the binomial model will give us. So this is a picture of the number of flyers who show up with a ticket, and I need to know a mean and a standard deviation because those are the parameters of a normal model. I need those numbers. I have formulas for those. This is a binomial distribution. I have formulas for mean and standard deviation of a binomial distribution. The mean in the blue book is n times p. If we have 275 people who could show up, probability that they show up is 0.95, then that is about 261.25. So the average number of people who show up with a ticket is 261.25, which is below average, which is below the number of seats that they actually have available. So most of the time, you're going to get people showing up and have enough seats. So 261.25 is the middle. Standard deviation we also need. We have a formula for that. Standard deviation of the number of seats is square root of n times p times q. Formula is in your blue book. So that's the square root of 275 times 0.95 times 0.05, which is pretty ugly. It's about 3.61. So of course we got some round off error there, but this is just a model. It's just an estimate. It's just a best guess. It's not going to be perfect anyway, so we're just going to let the round off error be there. Okay, so one standard deviation above the mean is getting pretty darn close to 360 or 265. I want to know the probability that they won't have enough seats. So I want to know where that 266 mark is, because 266 is the lower bound of when we're in trouble. Or actually anything over 265, we'd be in trouble. So maybe let's use 265. Anything bigger than 265 is a problem. So we want to know where 265 is on this curve. So 265 minus the mean, 261.25, over the standard deviation of 3.61. So that's a z-score. Where are we? Okay, let's compute that. So 265 minus 261.25 over 3.61, and that is about 1.04. Z equals 1.04. You also could use 266 as a boundary here, because 266 or more is a problem. I think you could probably logically argue that either way. All right, I want to know the probability of a z-score bigger than 1.04. So 1.04, so just barely one standard deviation above the mean. Anything from there up is over 265. So anything above 265 lies in there. The calculator is going to calculate that for me, because the normal calculations we can do. We don't have any huge exponents here. We don't have any huge combinations to compute. All we have to do is find area under a curve, which is a much simpler calculation. It's really just an algebraic formula. A little bit of calculus going on in the background. So menu, probability, distributions, normal CDF. The lower bound is 265. The upper bound is infinity, or some very large number if you don't have your CAS. And, I want to do z-score. So 1.04 is actually my z-score. That way I don't have to change mean and standard deviation. Okay, so that's about 14.9%. Okay, so this is equal to about 0.149. So there's about a 3% difference. So we had 11.6% using the binomial distribution. So we're, let's see, minus, let's see what the difference is. I still have it here on the calculator. There's a 3% difference between what the binomial model gave us and what the normal model gives us. And the reason for the difference is this is a continuous distribution. So you have stuff between 365 and 266 that doesn't exist in a binomial world. 265.1 is in this area. 265.2 is in this area. 265.3 is in this area. Those numbers don't exist in the binomial distribution. Only whole numbers exist in the binomial. Even if we move this over to 266, it's going to underestimate because it's a continuous model, whereas binomial is a discrete model, and the only thing we're considering is whole numbers of ticket holders. So they're always going to be a little bit different. But in the realm of predictions, probability, models that are not perfect at actually telling us what the real world's going to do, because the real world's messier than the models are, having a 3% difference is really not that bad. And so if you didn't have a machine that could compute the binomial model, the binomial probability, this is a good alternate way to do it. And on the AP exam, this is considered a viable method. You can skip straight to the normal model and use this procedure instead of doing the binomial, which the binomial is quicker to set up. So it's your better choice as long as your numbers will crunch. But this is an alternative that you could use as long as certain conditions are met. If you did the reading, you read about those conditions, and those conditions are summarized on the last slide. So let's take a look at those before we are done. The catch with normal is that it'll only work and give you a reasonable approximation if two conditions are met first, and you have to check. I fudged on that because I didn't check before I did it, but I knew it worked, so I went ahead and did it anyway. So the first is the independence condition. Either each person who holds a ticket probability of showing up to fill a seat is independent of other is not connected to anybody else's. So Bob, who has a ticket, and Joe, who has a ticket, and Judy, who has a ticket, their potential for showing up to fill their seat is independent. Like what Joe does is not connected to what Jill does, is not connected to what Judy does. They all are independent. Or the 10% condition will override if we're not sure they're independent, and 10% of 275 is 27.5. And sorry, let me back up. 275 people is less than 10% of the entire population of people who fly. So as long as we're looking at just 275 people, and that's less than 10% of all potential flyers, there's more than 2,700 flyers at an airport at any given time, usually. So the 10% condition is met. Condition 2, okay, so let's jot something down. So 275 is less than 10% of all potential flyers. As long as that's true, it really doesn't matter if they're independent or not. It's like the non-replacement thing. It's like if you don't put the M&Ms back in, as long as you don't pull out more than 10% of the M&Ms, you're still okay. It's the same principle. The other condition is that you'd have to have at least 10 expected successes and 10 expected failures. So you expect at least 10 people to show up, or at least 10 people not to show up. Well, and has to be true. So the number of people who are going to show up is 275 times 95%. This is N times P, which we've already computed. That's the mean of the model. That's the 261.25. That's at least 10. We expect more than 10 people to show up for this flight. 261 is way more than 10. And the number of people who won't show up for the flight on average is 275 times the 5%, which is the other 13.75 people. These should add up to the 275. That's more than 10. So these are both at least 10. And as long as both of those are at least 10, then the normal model will give us a pretty good estimate. Now, why that is true is beyond what we can deal with right now. Why this is true actually is related to something called the central limit theorem, which we don't learn until chapter 17. So for this, you'll just have to trust us for now, and we'll dig into why at least 10 is important later when we do some sampling and see what happens when that's not true and things kind of fall apart. So for now, you just have to buy it. This, using the normal situation in place of binomial, you can use as long as the conditions are met. But you can just get by with the binomial. On the test next Tuesday, as long as you can use the binomial, you're good. The normal is just a substitute if you prefer it. But you don't have to use the normal to replace the binomial if your calculator will do the computations. And I will never give you something for which the calculator won't handle the computations, nor will they give you something like that on the AP exam. Okay, just for funsies, there is one problem in the textbook. It's not on your notes here anywhere, but we're going to add it. On page 432, and scans of the textbook are on Schoology if you need them, if you don't have your book. I want you to give number 31 a go. My answer key is uploaded so you can kind of check against it. It's a situation where you could work it both ways and kind of compare the two. So it's very much like the one that we just worked. So add that to your chapter 16 homework set. And when I see you again, we should be able to turn that homework in and move on.